Hello, class. Okay, so we're going to talk about Newton's laws of motion. So previously, we started this course by talking about kinematics, which is the study of motion, where that was just descriptive, like if an object is moving in a particular way, where is it going to end up later? Or how fast will it be moving later on? But we didn't talk about like why things move in the first place. And that's where Newton comes in. He published his work in the year 1666, and this was one of the most important books ever written in human history. There was some work leading up to it, but what Newton did really kicked off the scientific revolution. And one of the most important scientists of all time, top 3 physicist easily, very, very smart guy. And we can, he wrote a very lengthy book describing, his theories on how things moved. And in particular, he was very interested in the solar system and gravity and planetary orbits. But we can kind of summarize his work, the foundation, in these 3 laws, which I kind of just stated here. The Law of Inertia. Second one I just wrote as an equation, F net equals ma. And the third one, forces come in pairs. Now again, what we're talking about now is the foundation of everything we do in this class. So this is a very important topic, and so we're breaking it up into a few pieces. Right now, we're just going to talk about the basic laws, like the foundation of it, what each of these statements means. And then we'll talk about like how to actually use Newton's laws later on. Okay, so we're going to start out with the law of inertia. Now, this law was actually discovered by Galileo, who was around before Newton. They say Galileo died the same year that Newton was born, but Galileo came up with this idea of inertia. What inertia means is that, you might have heard it, an object in motion tends to stay in motion, or an object at rest will stay at rest unless acted on by an unbalancing force. Actually, it means a little more, kind of neglected in the first part. An object in motion will stay in motion with a constant speed and in a straight line, unless it's acted on by an unbalancing force. So if you have an object that's moving, or say we have an object at rest, it's going to stay there, unless something happens to it. And if we have an object moving, say 10 meters per second, and nothing is acting on this object, it'll continue moving in a straight line at the speed of 10 meters per second. So the speed or direction will not change. Now, that's unless acted on by an unbalancing force. So let's go back to this first example. Say this is just a rock you find on the ground. And it remains, you see it's not moving. If you keep watching it, it's probably not going to start moving on its own. So we can conclude it's not being acted on by an unbalancing force, but that doesn't mean that there's no forces acting on it. We know for sure that gravity is acting on this object. So there's the force of gravity, which is pulling it downwards. However, and again, if the ground was not there, this rock would fall down because gravity is pulling it down, but the ground is pushing back upwards on this rock. We'll just call this the ground force, which is pushing up. And so these two are equal in magnitude. Like, let's say this is 10 newtons. This one would also be 10 newtons. We haven't talked about newtons yet, but we measure forces in units called newtons, obviously named after Isaac Newton. So, you got 10 newtons down, 10 newtons up. And forces are vectors. So if you have 2 vectors that are equal in magnitude but opposite in direction, like we have here, the net force is 0. And so this is not an unbalancing force. And so it'll continue just doing what it's doing, which is remaining at rest. Okay, so Galileo came up with this idea, and it was a very big deal. It might not be surprising to you because it's kind of common knowledge nowadays, but when Galileo discovered this, it was a very big deal because philosophers have talked about this before, going all the way back to Aristotle, and the ancients believed that the natural state of an object is to be at rest. So that is here on Earth. Now, if you look up at the sky, everything is constantly moving. If you go out at night and you see the stars, if you wait for a while, they're going to move. So, like if you go out early in the night, and then maybe at like 4 in the morning, the stars will have moved significantly across the sky. The moon, or the sun, good example, it rises and then moves across the sky and sets, and these things never stop moving. And so in the heavens, things are constantly in motion, but on Earth things tend to be at rest. Like again, so you have a rock here, and it's just going to sit there. If you watch it, it's going to sit there. Eventually, let's say you pick up this rock and throw it, and now it's moving. Well, what it's going to do is it's going to hit the ground and then roll a little bit and then stop. And so it will return to this state of rest. And so, the view for thousands of years leading up to Galileo is that things on Earth, the natural state is for them to be at rest. And you can cause them to move by exerting forces on them. But they will eventually return to their natural state, which is to be at rest. What Galileo discovered was a very big deal, this idea of inertia. And how he figured this out, Galileo was kind of a rare type of genius, where he would do these experiments that were kind of trivial, but he could make some amazing conclusions out of those. So like another scientist like that was Einstein. He would do these thought experiments where he would think about things that are, things that anybody could think about. But, he would come up with these amazing conclusions based on these simple observations. But getting back to Galileo, let's say we have this inclined plane, and then we have another one, let's say that they both have the same angle. So he did this experiment where he would roll a ball. Let's say he placed a ball at a height h, above the ground, let it roll down the incline, and then it's going to roll across the ground and go up the other inclined plane, and it's going to reach a height that's almost equal to h on the other side. You notice it doesn't quite reach its initial height, but it comes close to that. And, if you let it kind of just go back and forth, it's going to keep getting, less and less, and eventually it's going to stop moving. But he didn't conclude that it's going to stop moving because that's a natural state of it. He reasoned that there was something causing it to slow down. Something that we call friction. Friction was actually, I think the first one to talk about friction was Leonardo da Vinci, who wrote about and even came up with laws of friction before Galileo was around, so it's not an entirely new concept. So he said, friction is causing this to slow down, and that's what's going to cause it to eventually stop. But he figured if there was no friction, if we could remove that entirely, and again, you can kind of start out, you have like a rough surface, there's going to be a lot of friction, and it's not going to get up as high, but then if you have a smoother surface, it's going to go up higher. So he reasoned if you make this like an infinitely smooth surface with no friction, it'll return to its initial height when it rolls up the other incline. And he did more experiments, and he said, what if we change the incline, the angle? what if we make this one a smaller angle? What you notice is the ball is still going to try to rise to that initial height. Again, it'll fall a little bit short. But the angle of the incline doesn't really matter. If you can remove friction, it's always going to rise to its initial height. And so imagine making this a very, very small angle. This ball is going to travel a long time before it reaches its initial height again. And if you make it completely flat, it's just going to keep on rolling forever. And so, yeah, Galileo turned it around. Instead of saying it takes a force to keep something moving, but, if that force is removed, it's eventually going to come to a stop. Galileo said the natural state of something is to just continue moving at a constant rate in the same direction unless something causes it to stop. So he literally just flipped that whole idea around. And this idea of inertia, the tendency for things to just keep doing what they're doing, that's actually kind of an example of relative motion that we were talking about in the last topic. Like if inertia, if the ancient idea is that the natural state of something was at rest, that would contradict this idea of relativity. Because the whole idea of relativity is that you can apply the same laws of physics in different reference frames. And if you say an object is at rest, like that's a natural state, that means like there's this one natural reference frame where an object is at rest. But, if you just picture this ball rolling across the ground, if you look at it from its own perspective, it can say it's at rest and everything else is moving backwards. And so, this idea of Galilean, or principle of inertia, that's very closely related to the idea of relative motion. Okay, so it's often called the Galilean relativity, like what we talked about before. And that statement was later strengthened by Einstein in what we now call the theory of relativity. But anyways, that is inertia. That basically, just think of it, things will tend to keep doing what they're doing. So they remain at rest or just moving in a straight line at a constant speed unless something causes that motion to change. Okay, now the next law is F equals ma. Now this is one of the most important equations we will see in this class. And kind of because of that, we're not going to do much with it right now. Because we're just doing like an overall view of Newton's laws. And we'll be using this one a lot later. I will just point out that this is a vector equation. So forces and acceleration are vectors. And this is kind of the foundation of mechanics. Because if we combine this with what we've done before, if we know the force is acting on an object, we can find the acceleration. And if we know the acceleration of an object, then we can describe its motion. Now, in this class, we have to kind of restrict ourselves to the case of constant acceleration. So we would need a constant net force acting on an object, and then the acceleration would be constant, and we can describe its motion. But Newton's laws are more general than what we're doing in this class. This is just true regardless of whether or not the forces are constant or not. So that's very, very important. So don't think because we're skipping over it and not spending much time on it, that this one's not a big deal. It's actually a very big deal. But let's go to this next one. Forces come in pairs. Now this is very commonly referred to, we often state it as, for every action, there's an equal and opposite reaction. I'm not a big fan of saying it that way because just the words action and reaction kind of implies that like one thing happened and that caused another to happen. But I just think like forces just always come in pairs. And you can never isolate them. So to kind of demonstrate that, let's say we have two objects, A and B. they could be touching each other or not, doesn't matter. And the idea is, let's say object A exerts a force on object B. I'm going to draw it like this. I'm going to label that FBA. So that's the force on object B due to object A. So if this force exists, I'm stating this law that forces come in pairs. So what that means is if A exerts a force on B, B exerts a force on A. And it actually means more than that, but let me write this down. So this would be the force on A due to B. And these forces are equal in magnitude and opposite in direction. So let's say A exerts a force of 20 newtons on B. B exerts a force of 20 newtons back on A. They're always equal in magnitude and opposite in direction. So like say you're wearing roller skates or something and you go over to the wall and push on it, you're going to move away from the wall. So like you push on the wall pushes back on you. That's Newton's third law. Now, you might be thinking, okay, that's easy, let's move on. This law is very non-intuitive. And there's kind of a little tricky question that I put this on an exam once, and a lot of people got it wrong. It was a multiple choice question. So I figured, okay, we need to go in more detail in Newton's laws, Newton's third law in particular. And for some reason, students very often get this question wrong. So what I started doing is telling students, I'm going to put this question on the exam. And, but some students still get it wrong, even though I announce that it's going to be on the exam. So let's talk about the question first. Let's say we have an object. Just say this is a book that is resting on a table. So we know there's a force of gravity acting on the book. Okay? And if that was all that was going on, if there was gravity pulling down on the book's going to accelerate downwards. Here's Newton's second law. The acceleration would just be the force divided by the mass. It would accelerate downwards. But it's not doing that. Here, we've got a book. It's just sitting there. And so the net force on this book has to be zero because it's not moving. It's not accelerating. And so if the acceleration is zero, the net force must be zero as well. So there has to be an upward force. Now let's say the force of gravity is 20 newtons. We know that, we're calling this force table, F table, because it's a table pushing upwards on the book. And we know that also has to be 20 newtons, because if these were not equal in magnitude, like say this was 25 newtons, then the book would accelerate upwards. That didn't happen. I didn't set this here, let it go, and see it accelerate upwards. And we know it can't be less than that, or there'd be a net downward force, and it would accelerate downwards. It's just sitting here, so the net force has to be zero. So these two are equal in magnitude and opposite in direction. So the question is this an example of that Newton's third law, forces come in pairs? And the answer is no, it is not. And to be clear, this one here, we have two objects, A and B. So if A exerts a force on B, B exerts a force on A. So why do so many students say that this is an example of Newton's third law? The whole idea behind Newton's third law is these forces are equal in magnitude but opposite in direction, and that's exactly what we have here. However, just because forces are equal in magnitude and opposite in direction, that does not mean that's an example of Newton's third laws. These are not these paired forces that we're talking about. So we have to look a little deeper to see how Newton's third law applies here. And one key is that these two forces are acting on the same object. Where in Newton's third law, it's always like A exerts a force on B, B exerts a force on A. We have two separate objects. And these forces always act on these separate objects, these paired forces. So, but how does Newton's third law apply here? Let's look at this table force. Let's start with that. So, what force is paired with this table force? So, this is the table pushing upwards on the book. So, what that means is that the book is pushing down on the table. So, like, these two forces are paired with each other. The table pushes up on the book, the book pushes down on the table. So you can imagine if you, instead of placing a book, say you placed a car on top of a table. Gravity is so strong, like in order to support a car, the table would have to exert a very large upward force. And then the car would push back with that same force, which would probably cause the table to collapse, unless it's very strong. So, yeah, I mean, if the table is pushing upwards on the book is pushing downwards on the table. So these are two separate objects, the book and the table. So one of these forces acts on the table, the other acts on the book. What about gravity? So what force is paired with gravity? And again, we have to ask, where is gravity coming from? So gravity is coming from the Earth. The Earth is pulling down on that book. And so what that means is, say, here's the Earth. The book is pulling upwards on the Earth. So Earth pulls down on the book pulls up on the Earth. So these two forces are paired as well. The force of gravity between the Earth and this book. And again, very non-intuitive. Like, let's take this this cap here. This has a mass of, I'm going to say, like 2 grams. Now, the mass of the Earth is around 6 times 10 to the 27th power grams. It's a little bit bigger. Okay, so the Earth is pulling downwards on this cap. So this enormous mass is pulling on this cap. And the cap is also pulling on the Earth. The question is, which is pulling harder, the Earth or the cap? And the answer is they are pulling with the exact same force, equal and opposite. This is Newton's third law. So this cap is pulling on the Earth just as hard as the Earth is pulling on it. I think most people, if they never took a physics class, would get that one wrong. You probably think the Earth is pulling a lot harder because it's bigger. So another question, if I drop this cap, it's going to fall. I'm too lazy to pick it up. Here, I'll just drop it. Okay, so it falls down. Now, did the Earth rise up to meet the cap? Well, technically, yes, it did. It had to, because, the cap exerted a force on the Earth. And so there's an upward force on the Earth. It had to accelerate upwards. What is that acceleration? Well, that would be the force of gravity divided by the mass of the Earth. And I'll tell you, in this case, the force of gravity, if you have a mass of 2 grams, the force is going to be around, let's see, 0.02 newtons. And that would be around 6 times 10 to the 27. I'm going to convert this to kilograms. So 6 times 10 to the 24th kilograms. And a newton over a kilogram is a meter per second squared. So this would be around, the acceleration of the Earth would be around 0.003 times 10 to the minus 24th. Let's see. So, rough estimate, the acceleration of the Earth upwards is around 3 times 10 to the minus 24th power meters per second squared. So you're like 0.000, you've got 23 zeros and then a 3. Now if you look at, V equals V naught plus AT, if the Earth was, say, at rest, say it took 1 second for this cap to hit the ground, then the velocity of the Earth upwards would be around 3 times 10 to the minus 24th power meters per second. Could you possibly detect a velocity that small? No, I don't think we could ever detect a velocity that small. So, we don't notice the Earth rising, but technically it has to rise, at least according to Newton's laws. Now, on the other hand, the cap certainly fell and moved because the mass of the cap is small, so that was a large acceleration, and it's going to fall a noticeable amount. Okay, so Newton's third law, not very intuitive. It might seem simple. A exerts a force on B, B exerts a force on A, but there's a little more to it than that. Okay, so I think we'll stop this video here, but there's some time we've been talking about forces, and what are forces? But I'm going to do that in a separate video. So this one we'll just talk about Newton's laws, and then we'll talk about what forces actually are.